So for the cohort study, we start with the population and end with the outcome. And for the case control, we start with the outcome. We have some patients with heart attacks and some of them without. And we ask them, did you take that pill? Okay, and we found out that the percentage here is higher than here. Okay, so we can move on to the plan of for today. First, we will start with the types of PICOs. Okay, we discussed in the first lecture what is the PICO, but we have different PICOs. Okay, and we will know those different PICOs. How can we answer these questions? And in the second part of the first part, we will discuss the data types again and how to report them in tables and in graphs. And when we move on to the second call, I hope we can finish this in the first call, and the second call we can move on to the null hypothesis, the alternative hypothesis, and the two types of error. Okay, the most important thing today is repetition. Okay, because when you ask me in the third slide, I can repeat 3 slides, and this is easier for me than repeating 10 slides, and it will be easier to repeat 10 slides than repeating 50 slides. Okay, so please just stop and join the audio and tell me, just repeat from that slide, because if we move on, it will be harder. Okay, if you are ready, okay, we can start. Does anybody has any problem with the connection with anything? Okay, I think we can start. I'll take those 2 slides from the last presentation. Here we have the types of questions. Okay, we have therapy. We are intervening with the therapy, and we want to know if this intervention is effective or not. A second type is a diagnostic test. I go with the diagnostic criteria and I ask if my diagnostic criteria is assessing the patient in the best way, according to the golden standard. Okay? Prognosis. How severe is this disease? How many will die in 10 years, in 5 years, in 2 years, in 1 year? Okay? This is a question, and this question is quite different from the intervention question. Okay? Harm or etiology. Okay? Here we are finding about the exposures that cause that effect, the disease we already have. Prevention. We are intervening, but not to treat, but to prevent the occurrence of that disease. Cost effectiveness, and those cost effectiveness and quality of life are not so frequent, but they are becoming frequent, because nowadays we have a lot of interventions, but we need the intervention that is mostly the best in cost effectiveness, or the best regarding the quality of life of those patients. Okay, so those are the different types of questions, and if you can see, they are quite different. So to assess them, we need quite different study types. Okay. Can you see this slide? Is it clear?
Yes.
Perfect. Okay. For therapy, what do you think is the best intervention? Or let me just take it down. Okay. What do you think the best study type to do? I will open the chat, and just please send in the chat, or just unmute yourself and talk. What is the best study type to assess an intervention? I have a new job.
RCT.
Exactly. If we can do an RCT, if it is a surgery, what should I do?
What do you mean?
If I have my intervention is surgery, okay? and this surgery is truly effective. Okay, I believe it will be effective. Okay, I brought the patient. Is it always ethical to do an RCT if we don't have any
No.
other drug to compare to? If we don't have any prior intervention, for example, for COVID-19, okay, the first trial should be
we should start from the outcome, which is COVID-19. So it's the controlled case control.
Okay, for the first phases of intervention, we use usually small controls or case series. Also, we intervene on those patients with this new drug. And afterwards, if we have this drug, okay, like we have the toxicity, we have the efficacy, we can compare it to other things. And here we apply a clinical trial. This is not always the case, okay? Sometimes from the first step, we start with an RCT, but remember that we have those two options, okay? Either I come to the groups and divide them into two and give the first part or the first arm the golden standard, the intervention I already reserve to those patients, and my new drug to the second arm, and I compare them. This is the usual case, and we have some exceptions. Is that clear?
So we're saying that we are starting with case series?
No. We are starting with randomized controlled trial, okay?
No, I mean in the case of COVID-19, for example.
No, for COVID-19,
not
they
in general.
already started with the RCTs.
Okay.
Okay.
So when do we start with?
Like the intervention I told you about. Okay. If I have a really severe disease and I don't have any golden standard, okay, I already have some antibiotics or antiviral drug that I can preserve to those patients with COVID-19. I don't know the efficacy, but I know that there are antiviral drugs, okay, that might be efficient, okay? So I'm starting with them. So if I'm starting with already known drugs, I can do directly an RCT. But sometimes if I don't have any previous intervention, okay? If I'm starting with, I have a disease and this disease is severe and I don't have any intervention and somebody came to me and gave me some herbal medications, what should I do? I should try them first, okay?
On a little group of people, yes.
Phases of, sorry?
Yes, I should try them on a small group of people.
Okay, and actually, first, if we have that drug that wasn't reserved to patients or to humans before, we should start with the 4 phases of clinical trials. The first phase is trying them on a very little number of healthy controls, okay? I just invite some healthy participants, humans, and I ask them to take this drug because I want to assess the toxicity, okay? Then in phase 2, I invite some patients, okay? And those patients, I need to assess the efficacy, okay? I need to assess if I give them this dose, will that be efficient? Okay, will that treat this condition? Because in the first case, I just assessed the hepatic toxicity or the renal toxicity. For the second phase, I went to them and I asked them, have you been treated with this drug? And this is efficacy. In the third part, I compare this drug to other drugs. And for the third part, I have the RCTs, okay? For the fourth part, it's cohort study. How we issues the approval, the FDA approval to this drug, and it gets manufactured and gets into the market, and everybody takes it. And after that, we ask, is there any side effects?
There is any adverse, yes.
Exactly. Those have very little proportions or prevalence incidence. Okay, so those are the 4 phases before I go with the new drug. But if I already have some drugs that I know that might be efficient and they're not so risky for the patients, I can start with the RCT. Okay, I can also do like if it is not intervening with the first intervention, for example, if I'm giving for migraine some kind of NSAIDs, and the new drug is a herbal drug. Okay, so I can give the 2 groups NSAIDs, the usual NSAIDs, and I add to one of the groups that herbal drug. Okay, so I can do this as well. Okay, if this is fine, we can move on to the diagnostic test. What should the diagnostic test, what should be the study type of a diagnostic test? Please answer.
Here we are starting from the risk factor, and we need to see if we get to the outcome or not.
No, in this diagnostic test, I have, for example, a diagnostic criteria, or I have a questionnaire that can expect if that patient has a mild depression or advanced depression or major depression. I have a blood test that can predict some kind of disease. So what should I do?
Okay, if it's a questionnaire, a cross-sectional, if we are going to use a questionnaire.
Yes, usually cross-sectional studies have questionnaires, okay? But not all questionnaires should be cross-sectional, okay? So I can do a questionnaire that is not cross-sectional. For example, I use questionnaires for prospective cohort studies. I collect those cohorts and I ask them each time with a survey. Yes, Lina?
Ibrahim, here it's also the same. It's still a trial, but now I'm not trying medication. I'm trying tests, so it's also RCT.
Also RCT. And is there any other option?
An interventional study, like.
Can it be a cohort study?
Yeah, cohort, right? Cohort. That's right.
Okay. So
prospective
as
cohort.
you said, prospective blinded control comparison of the gold standard. Okay. A blinded and controlled, so it is exactly the RCT. Okay, but we can say an RCT because the T means a trial, so intervening, but without the T, it looks like this. Prospective. Okay. So for prognosis.
So for the diagnostic test, you said which type of studies?
It's randomized, should be randomized. It should be blinded, okay? And I have a group of those who have the disease and a group of those who doesn't have the disease, because I need to assess the specificity and the sensitivity, okay? So if I combine all those, what should the study type be?
I'm sorry, but I have interrupted connection, so I haven't actually heard you. But,
yeah, of course. Okay, I can repeat it. When I'm assessing a diagnostic test, I need several things. First, I need a group of those who have the disease, and I for sure know that those have the disease. And for the other group, I need those who do not have the disease, and I'm 100% sure that those do not have the disease. Is that clear?
Okay.
Okay, so I need two groups, and I'm intervening with my intervention. Not my intervention, I'm intervening with my diagnostic test, okay? So the best way is getting them together, applying my test to each group of them blindly, so I know the sensitivity and specificity of my diagnostic test. Because when I apply it to those who have the disease, I will know the sensitivity, and when I apply it to those who doesn't have the disease and I have some false positive cases, so I will know the sensitivity. Okay.
So it is a trial.
Sorry.
It is like a trial.
It's exactly like a randomized controlled trial, but without the trial name, because trial means intervention. Okay.
Okay.
Okay. So for the prognostic studies, what should my intervention be? My study design be?
Cohort.
Cohort is a very good one, of course, because I'm getting my a group who have the disease already, and I'm assessing if they are having mortality, any side effects. Of course, that's right. But do you think, Nawara, that there is any other option?
Case series. If I'm following patients who have the same.
Okay, both are right, but case control, I would prefer case control first. Why? Because for case control, some of my patients died. Okay, so I collect them, and I collect some of those who didn't die, and I assess what happened to those and those. Okay, if I'm assessing a case series, it's exactly the same, but without the control group. Okay. So I have an additional arm that I compare to when I'm doing a case control, which is better. But if I don't have that group, I will do a case series. Okay?
Okay. So we can do a case control or case series or cohort?
No. For each case, we have the better option, and we have like other options. But of course, if I can do a cohort study, I shouldn't do a case control one. Okay, we go to the pyramid, to our pyramid, and we take the best one. Okay, if we have no difference, the three of them are applicable, we take the best, and the best is a cohort. Second is case control, and third is a case series. Okay.
Okay.
What is the benefit of a cohort study on case control studies? Actually, for a cohort study, I can assess the prevalence. Okay, I can say that this side effect will happen in 20% of those patients. For case control studies, I can't say that because I already just took those 20 and I compare them to 20 other patients. Okay, but for the cohort studies, I took the 100 and I said that 20% of them usually have the disease, get the side effect, I mean. Okay, so this is the benefit that a cohort study has and that a case control doesn't have. Is that right?
Yes.
Okay.
Yes, it is.
Perfect. So another one, actually harm and etiology is really similar to the prognostics studies. So I'll skip it. It will be exactly the same. A cohort, case control, case series. Of course, they put here RCTs, but this RCT, I shouldn't plan for this RCT. It can happen, but I shouldn't plan to do an RCT when I'm doing something harmful. How does it happen? Usually, I give a therapy and I assess my intervention. So I have a good intervention and I feel that this is a promising drug. I intervene with this drug and suddenly I have more side effects than the other arm. So what is this study after all? I started with the therapy study, but I end up with a harm study, right? Because my drug started with a promising drug and ended with a harmful drug. Okay, so we have an RCT here, but it's totally unethical to plan for an RCT where we have a harmful intervention. Okay.
Okay.
For prevention, actually prevention is really similar to therapy. Okay, so if I have an intervention that can prevent the disease, I should apply it with an randomized controlled trial. Of course, if it is really promising and I don't have any doubt in that, I shouldn't do an RCT because I'm prohibiting the other group from getting this drug, okay? So for the cost effectiveness and quality of life, I will not go through them because they are so rare, and I don't think we will plan to do
Okay,
anything.
just a second. So when we're talking about prevention, if I'm not going to do an RCT, what am I going to do?
If I'm applying my
try
example, like adding iodine to this salt, okay? What is this study? If I'm adding something to, exactly. If I'm adding prevention, sorry, somebody is like, just tell me if I need to go somewhere because you are writing on my screen. Okay. If I'm adding an intervention that can prevent an outcome to everybody, it's a cohort study. Okay.
Okay.
Because I'm not assessing my intervention. I'm assessing the outcomes, as the example you sent to the group before.
Okay. There is a question on the chat. Rama is saying, what about cross-sectional for harm?
As we said before, a cross-sectional cohort is better than any cross-sectional here, and it's similar to a cohort because it takes the higher degree. Okay, if I have a cross-sectional cohort study, it will be as high in evidence as the best part. Okay, so it can just sit here, but of course for cohort studies we have several types. We have the prospective, retrospective, and everything. So we are not going to put them all in this line. We just put the main type. Okay. Okay. So we will return. Okay. Just
another question.
Yes, please.
Rama is saying, is cross-sectional like a subtype of cohort?
It's not exactly a subtype of cohort. Cohort study, by definition, is assessing the patient from the start and continuing to assess them longitudinally till I don't know what it is, the timetable of the disease of the study. But for cross-sectional study, by definition, is not assessing the patient longitudinally. Okay, I just assess them at a single moment in time. Okay, so it's not exactly a type of cohort studies, but yeah, it's quite similar because each one of the assessments of a cohort study is like a cross-sectional study. Okay. So if we move on, we will start with categorical data. Categorical data is as difficult as this. We just have two types, whether it is dichotomous, or three divisions of this pie, or more, but it's always like this. Categorical is exactly as similar as this. And if we start with the formulas, because we are having a statistics course, this one and the first one should be this, the percentage formula. And this is the central formula for categorical data. We have the part, and we have the whole, and we have this percentage. I believe it's quite easy, but it's really fundamental for the next slides. If I have a sample, I went to one of the hospitals and I asked them how many of those patients were wearing a mask for the last 20 days. Some of them said yes, some of them said no. So how should I present this? I present it like a percentage or proportion. They are quite the same, but when I normalize to 100, it's a percentage. When I don't normalize to 100, it's a proportion. When I say 13 out of 30, it's a proportion. And when I say 30%, it's a percentage. Okay? That's quite easy. But when I go to 2 or to 3 hospitals, and I say those hospitals represent the whole population of hospitals in my city, should I just say the percentage is like this? I believe we shouldn't do that. We should add a number. We should add a number. How sure are we about this percentage? Do you agree or not? Do you understand the difference between this case and this case?
No.
In the left case, it's quite easy. I have the population. I have the whole population that I'm reporting. I have 100 patients and 30 of them were wearing masks. When I went to the other case, I took a sample of 3 hospitals out of 30 hospitals. And I'm saying that according to those hospitals, 30% of our patients usually wear a mask, but I'm not quite sure. And by I'm not quite sure, I mean that there is a little bit of uncertainty in my answer. And when I'm saying a little bit of uncertainty, I should add it to the number. I say 30% plus minus.
Plus minus.
Exactly. Or I put 30%, but it can go from 20% to 40%. Okay? Those two options means that I'm representing something bigger than I can handle in my assessment. Okay? So,
okay.
Please ask me all the questions you already have for this part, and we can continue with the other slides in the second part of this.
So this means we use confidence intervals only when we want to generalize our information?
Exactly. When I have,
So
if I have all COVID-19 patients in the world, I won't say that I have a confidence interval because I'm 100% confident of my results. I'm 100% confident that 100,000 of COVID-19 patients died. Okay, so I don't need a confidence interval. But for example, if I have that that mortality rate for flu, and I'm not quite sure in Africa what is the number, and in Europe what is the number. So I take a representative sample. I take one hospital in Africa, one hospital in China, one in America, and I combine them, and I say I have a confidence interval of that much. Okay, is that clear?
Yeah.
Perfect.
There's a question in the chat.
Yes, please.
Massa is saying, in a population, I can't control all the samples 100%. That's why I need a certainty percentage, which is represented by confidence, right?
Exactly. This is what I'm saying. Exactly.
Great.
Okay. So we can end this call, and I'll call you in 20 minutes, not 20 minutes, in 10 minutes, and we can start the second part. Is there any...
Can I ask a question about the diagnostic studies?
Yes, please.
You said that I need to get two groups, a group of patients and a group of healthy persons. So can't I just try both interventions or diagnostic tests on the patients only?
But I want to have the sensitivity. The sensitivity means how many of those with negative results will have positive results in my test. Okay? How many of those who do not have the disease have positive results in my test? Okay? So I can test the sensitivity in your way, but I can test the specificity, which is quite important.
Oh, that's why I need healthy persons.
Exactly.
Okay.
So
much better. Thank you.
You are so welcome. See you in 10 minutes.
See you.
Okay, maybe you can start. Okay, is there any other questions for the first part? Please mute the mics so we can start. Okay, we are talking about categorical data. Please mute. Yeah. Okay, we are talking about categorical data. We say that we have this pie chart, we have the percentage formula, we have a sample that represents everything I want, and a sample that represents the population. Okay, here we can find a table for the characteristics of one of the papers we already discussed. Okay, what do we see here? Cold weather, well, we have exposures, and for reporting the exposures, they said for cold water, 42 patients were exposed, and they present 100%. You can see here what this number represents, the number, the actual number, the accurate number, and here the percentage. Also here, wet environment, 35%, 35 patients, 83%. Okay, so if you go on, we can see here, for example, for cold water, we have just 1%. Why? Because we know that those with no cold water represent 0%. Those who were not exposed to wet environment represent 17. Okay, but here for duration of exposure, we have to put all the categories. So if we have just if we have just two categories, we can just put one. Yes and no, we can just put yes. But when we have several categories, we should put several numbers and put several percentages. Is that clear till here? You can just put the sums, the clapping, anything, so I can, okay, perfect. But this...
No, I didn't get what you're saying.
Okay, for cold water, I don't have several categories. I just have those who are exposed to cold water and those who are not exposed to cold water, okay? For those who are exposed to cold water, they are 100% and they are 42. I put them. Do I have to also put those are not those who were not exposed to cold water in another line and put 0? No.
No.
We can conclude that from here. But for example, for duration of exposure, if I just put less than 1 hour, would you know all those?
No.
Okay.
Okay, got it.
That's
okay.
why I need to put all the categories if you have several, and I just put one if I have two.
Okay.
Okay. This is not always the same case because for this table, we just have one population because I do not have two columns, but for case control studies, for cohort studies, when I'm comparing exposed and not exposed, okay, I can have several other tables. For example, here, I have an intervention group. This is an RCT. I have an intervention group and a control group, okay? And I have a categorical variable. So how will this categorical variable be applied here? Okay, it will be applied for each patient, either yes or no, okay? Or if we have 3 colors, there will be 3 colors here. And for the control group, in the same way. So now I don't have any 1% that can represent the population, okay? I have 2 numbers for each group of participants, okay? I have for those intervention group event and non-event, and event, non-event for those control group. How should I represent that? With this table. This table is called 2 by 2 table. This is very important for categorical data. What does 2 by 2 mean? For this variable, the event, I have 2 outcomes, event or no event. And for the intervention, I have 2 options, intervention or control. So if I multiply them, we have 4 cells, okay? Here we have the total. The total is just putting those 2 groups together, but I'm saying about the core table. The core table includes just 4 cells. Is that table so easy to you or not?
It's okay.
Okay, so we will use this table to answer all the questions about categorical data. Okay, so for example, here we have that table. We are discussing the characteristics, but here we are just putting them in different groups. Here we have 2 groups, males and females, okay? And we have a professional training group and peers training group. Can anybody tell me where is the 2 by 2 table? Hopefully that one who was like putting line on my screen can put a line now.
Can you repeat the question?
I need the 2 by 2 table. Yeah, he or she did. I needed the 2 by 2 table. Where is the 2 by 2 table? The 2 by 2 table starts from here. We have 2 options and 2 options. Sorry, Nawara, I'm not hearing you very well.
I was just pointing at the 2 and 2 table.
Exactly. So we have them and we have the p-value. We are not discussing this column now, but we will discuss it, okay? So now we know that we have p-values to compare those groups. Okay. For this study year, okay, we have 3 options and 3 rows, and we have just 2 columns. So it's not called a 2 by 2 table, but it's quite similar to our 2 by 2 table. Okay, it's a 2 by 3 table, but it's quite similar. Is that okay?
Okay.
Okay, now we move on to this. If you remember the pie chart, in the pie chart, I can't put 2 pies on each other, okay? So how should I represent those numbers if I have 2 variables with 2 percentages? For example, here you can put in between brackets the percentage, but this percentage and this percentage, if we just put a plus between them, it will be 100, okay? And if we combine those two, it will be 100. Okay, so how should I put them into a graph? I use this clustered column graph. How do I do it? I have, for example, here the 2017, and this represents, for example, gender. Okay, males and females. Males are like 140 and females are 80. Okay, this is how I represent my variables. For example, for study year, I might have 3 columns, okay, and so on. Is that clear?
Yes.
Okay, perfect. So we are done with categorical data, and this is all we need just before the statistical tests. And if we understand what we already discussed, the statistical tests will be so easy to understand. Okay, so if we move on, we can't go back. So please, if you have any answer, please just.
Okay, so to summarize, in the categorical data, we can only use pie chart or bar chart, right?
Exactly. Of course, you have other charts that can be discussed. For example, you can have those columns that are divided into several categories, but they're all having the same concept, okay?
Okay.
In Excel, you can have 100 charts for these data, but they are quite similar. If you understand the concept, how should I put them? If I just have one variable, can be divided into a pie chart. I can't have a pie chart with several variables, okay? If I have, but of course, I can have one variable with this chart. If I just hide those on the right, I just have this one. It can be the case, but it's not quite common. If I have one variable just having 2 columns in a bar chart. If I have several, I should use this cluster chart and so on. Okay, but by the common sense, you will understand if this chart is good, is not good, and you will find a better chart. You can try several charts, but you need to understand the very basic way, and you can build on your experience. Okay.
In the
Yes, please.
In the previous chart, weren't we dealing with the same variable but for different years? Like the variable was dolphins or whales, so it's one variable for different years.
Exactly, exactly. This graph is not actually related to this, but I can represent those in a similar way.
But it is still one variable, right?
Yeah, I have one variable, which is categorical, whales or dolphins.
Okay.
Here we have one variable that has males or females, and how many of them are in professional training group and how many of them are in the peer training group. Here we have that number, but I don't know maybe who swim and who doesn't swim, maybe like this, okay? So I have one variable here and one variable here, but this variable here has two options.
Okay.
Okay, so we move on to numeric data. Is there anything? Okay. Numeric data is as complex as this line. It's so complex, as you can see. We have continuous data that we should put as dots on that line, and if we have any additional patient, we will put it here, here. Okay, so, but if I have 1,000 patients, will this line do the work for me? Not really, because I will have several dots in the same place, and I can't see them. So how should I put the line now? If I take it and put it horizontally and put another axis, and for the other axis, I put the frequency of having this measurement, okay? It's like this. For the 5, I don't have any frequency, no patients are here. But for the 15, there are several, sorry, those numbers doesn't mean anything, but yeah, this is an example. You can put here 100, 200, 300, and so on. So if I have 600 patients, I will have a column that high. If I have 100 patients, I will have a column that, as high as this. Is that clear till here?
So the Y column is for frequency?
Yes, exactly.
Okay.
Okay. But if I have those columns, this histogram, how do we know the histogram from the column or the bar chart? Those are just adherent to each other, okay? But if you remember this, those do not match, okay? Each one of them is a separate column. But here, sorry, in here, we might have a number right quite in here or like exactly on the line here. So I need that, okay? This histogram just divides them into bars just to know how to put the column. But in the quite accurate case, I should have lines, not rectangles, okay? I just divide them into more columns, and I will be more accurate. Okay. For example, for that column, I might divide it into 2, and one of them is as high as 500, and the other one is as high as 700. And because I just combined them into one, I have this. But it's more accurate when I have smaller bars to do the histogram. Is that clear? Okay, perfect.
This is particularly useful for continuous data, I might suppose?
Exactly.
Thank
because you can't have them like this while this is not continuous. If you can see, it's from 0 to 50. It's continuous. Okay.
Yes. Okay.
Okay. So how to report them? We have age. Age is continuous. I think you all agree. So we have the mean and the standard deviation. If I go to here, how should I represent this in a table? If you want me to just tell you something that can represent this graph in two numbers, what should I give you?
Mean and standard deviation.
Okay, the mean says where this distribution is standing. Okay, the mean is right in the middle. If it is like symmetric as this. So if I say the mean is 25, it's different from if I am saying the mean is 50. You know where the distribution is. And what does the standard deviation give?
So we have to divide it by the standard deviation. So we will know first the mean, and if it's normally distributed, so the mean, median, and I don't know what the mode, they will be a ball in the center, okay? And after that, divide using the standard deviations. So one standard deviation is 66.8, and
okay, but what does that mean? If I give you the mean, I told you where this distribution stands, but if I give you the standard deviation, what does it tell you?
It means how much the data are far from the mean.
Exactly. It says how the variance is, how wide is this distribution. Okay? So if I know how wide is this distribution and I know where is it standing, so I know how the distribution looks like. Is that right?
Yeah.
Okay.
Yes.
So we can move on. For each number, we are giving a mean and a standard deviation. Standard deviation usually is a smaller number than the mean. Okay, but here you can see another number. It's called the confidence interval. We will discuss this, okay, in the next slide or the next slides, but confidence interval is a number that can be taken from the standard deviation. Okay, so for each one of those outcomes, I have a mean and something that can represent the variance, how the distribution looks like, and where is this distribution standing. Okay, okay. For now, we can see here that the age is represented for everybody, but for smokers, we can put different distributions for different categories. Okay, so we just divided the patient. We have those small distributions and those big distributions that represent the whole sample. Okay, is that clear? This is just a continuation of this table, nothing important here. We just have standard deviations and means. This is how I should represent continuous data in a table. Okay.
So both standard deviation and confidence interval represents the variance.
Exactly.
Right?
Exactly.
Okay.
So it's not acceptable if I give you just the mean and I tell you I have a sample with the mean age of 23.6. That's pointless because you can't understand how does my sample look like. Okay. Now we should look at those. Those are representatives of different distributions. Okay, I can have that pointed high distribution and those flat ones and this like wide one, and they are all fine. Okay, but this causes confusion right? So what
Right.
should I do? If I need to compare those or work with them, it's quite complex if we compare it to just the 2 by 2 table. 2 by 2 tables are always the same, but those are not always the same. What should I do? First, we should understand two concepts. The first one, if I take this purple distribution, okay, and just multiply my sample, how should it look like? Where will it go?
Multiply the purple, and he will multiply it. The blue.
Remember the line. What does the line represent? The line represents that for the 0,
it will go to 1.
It will go to 1. Okay. I don't mean the number. I just need how will it look like if I multiply the number of participants of that flat distribution.
The same.
It will concentrate the participant in the middle, so the mean will go up and the periphery will go down.
Okay. Okay.
I think it depends on the scale.
Two answers. Okay. It will stay the same, or it will move up in the middle and down in the periphery. Okay.
It's not about the number of your participants. It's about
according to distribution. Yeah.
Yeah. Just please 1 minute. Yeah, please, Maya.
It's not about the number of your participants. It's how they are distributing around the mean. Okay. So if you are taking the same sample exactly with the exact distribution, so I will have the same shape.
Okay. Okay. If yeah, please, Zara, can you talk?
Just like she said, if I can't answer the question because I don't know the new participants how they are distributed.
They are quite similar. The same participants. If I just take those,
okay, it will look
and
the
those.
same. It will just go up, but it will stay kind of the same.
Okay, just let us just divide it into parts. Okay, I will put this here. If I take those and those, will they be like this, right? Yeah, maybe this. Okay. If I take those thick ones and those thick ones, shouldn't they be like this? Because those are both thick and those are both thin. So the difference will be, if we have just half a degree difference here and half a degree difference here, we will have 1 degree of difference here, right?
Yes.
Okay, and this will be the same. So if we compare those to those, I believe that the answer of Maarouf is right. It is higher in the middle, but it's also higher in the periphery. But the difference here is this is higher more than this. Those are not going down. Those are not going down. That's false. But when this is coming up, if I compare those, they are going down. Okay?
So it's the same shape, but going up.
Yeah.
Yeah, of course, it's all going up, but the speed of going up in the middle part is twice the speed of the periphery.
And why is that?
Yeah, why is that?
Why is that? Because I'm just combining them.
Yeah, if you are combining them, so the difference between the highest point and the lowest point will be the same. So we will have the same shape, but it will be exaggerated, like.
Okay, just let me tell you, if this is half and this is half, this is 1, right?
Right.
If this is 1 and this is 1, this is 2. Okay, so
Yeah.
what is the difference between 2 and 1? 1. But here we have half and half, right? So here it is growing more in the middle.
Now it's clear.
Okay, so we should understand that the periphery is multiplying, but the center is going up in a higher speed.
Now it's clear.
Yeah. Yusra is clear about it. Zara, are you clear about this?
Yes.
Okay.
I don't know.
Yeah, please. Okay, just let me just say it in another way in the last time. Okay, I have this distribution. I added another one to the top. It will not go like this. No, it will go like this. Why? Because it's already convex. If I add convex to another one which is convex, it will be more convex.
Okay, I get it now.
Okay?
Yeah.
Okay, so if I multiply, they will be more convex. So if I add twice, it will be higher than like this. If I do the same another time, it will be high like this. Okay, this orange line is twice the blue one. But why is it going down in the periphery? It's not the same scale. This is a changing from each one to another. Okay, so when I put another purple line to this purple line, it's higher like this, but they just push it down, put it on the push it down. I mean they just took the numbers downstairs. Okay. So this blue line should be here. If I multiply the purple line by 2, right? But it's not here. Why is it the blue line not here? Because I moved the numbers down. Okay. Okay.
So you mean that these different curves are not on the same scale? The y-axis is different.
Exactly. Exactly. They are not on the same scale. If they are on the same scale, if I multiply the purple line by 2, it will be, I will start here, it will go like here. Do you agree? Okay. I multiplied this by 2, and I multiplied this by more than 2. Actually, I'm exaggerating. It's like this. Okay, but they pushed it down by moving the number down. So this is why this line is moving down, but it's not moving down in the real case. Okay, they are moving up, but they are pushing the scale down. Okay.
Mm-hmm.
Okay, I hope this is fine, and we should move on.
Dana is asking, why don't we use the same scale?
Because it can't fit on this slide.
So you're confusing us because it can't fit in this slide.
Exactly.
Thank you.
Okay. If we move on, okay, how can
you have a clear button somewhere?
Perfect. Now we know who was drawn on my screen.
No, not me.
Okay, so this is actually the first concept. This is the first concept. How? If I multiply, the distribution will grow higher and the periphery will be smaller, not smaller in numbers, but smaller in comparison to the middle part, to the mean, okay? It will grow faster in the middle and to a lower extent in the periphery. The second concept is the normal distribution. How can I make a distribution normal? A normal distribution has two things to do. The first thing is, where is it? Okay. I'll tell you how to do it, but just after we understand this is the mean, and I believe everybody can calculate the mean. None of us will calculate the mean in this course because the programs will do it, but we should understand what does the mean means. Yeah, the mean is combining everything and dividing them on the number. So if I have just one number that's quite low, if I have a 0 here, it will move the mean. Is that right?
Yeah.
Okay. What about the median? What is actually the main concept in this slide? We have mean, median, mode. They are representing where our distribution is standing, right? All of them stand in the middle, okay, or usually in the middle. So if I move them, I'm moving my distribution. So those are not similar to the standard deviation or confidence interval, but mean, median, and mode are quite similar. They are representing the main point, where is the center of my distribution. Okay. If you agree, the mean is affected by the outliers. Those numbers that are quite low or quite high affect the mean, but they can't affect the median. Why? Because in the median, I'm just ordering them and I'm taking the middle number. If I have this number like 0, or if I have it minus 100, it's similar because the median is still 5. Okay?
Okay.
So if I have two numbers, I'll divide them by 2, I'll combine them and divide them by 2, and I'll take the mean of them. What about the mode? We don't usually use the mode. We usually use the mean or the median, as you already experienced in our papers. Actually, I showed you the papers before we start, so you understand what we are talking about, just not to understand the theoretical meaning of them, but we should know how to use them before understanding them. So we know that we usually use the mean and the median, and we saw that in the papers. What about the mode? Actually, if the first number or the last number is just repeated several times, it will be the mode, okay? The number with the higher frequency, okay? But usually, the number with the highest frequency is in the middle, okay? According to the Gauss distribution or to the normal distribution. Now, we should know the first one of the characteristics or the things that make our normal distribution distinct. The most important thing is the mode, median, and mean are all in the middle. Do you agree?
Why do you assume that the mode will be the number in the center or in the middle?
Okay, if I give you, if I just cross those and I give you this distribution, what is the number with the higher frequency?
the two bars around the dashed line. Ah, I got it now. Okay.
Okay, so
Okay.
this number is the median because it stands in the middle. The distance from here is similar to the distance from here. It is the mode because its frequency is the highest, and it is the mean because if I combine all those and divide them on the number, it will be this point. Okay. Okay. The other thing this distribution should do is the dispersion. Dispersion should be the same because if I give you those three lines, okay, they all have the same mean, and they all have mean, the mode and the median in the same point. Do you agree or not? Please just tell me.
Yes.
Okay. If you agree, do you agree that the three of them are normal distributions?
No.
Okay. Then what is the difference between them now?
No, wait. So the normal distribution is the bell-shaped, right? So
exactly.
When we have the exact percentage, the fixed standard deviation and the fixed number of my population between two standard deviation, right? So when I have
exactly, Maya, you are talking about the variance. So you are saying we shouldn't just control the mean, median, and the mode. We should also control the variance. Okay.
So because if I will consider C a normal distribution, okay, so actually it's not, because if I will divide the variance, so I will not have 95% of my population between the two standard deviation, right?
Exactly.
Yeah.
Okay. So for the variance, we are going to talk about several numbers as we talked about the mean, median, and mode. For the variance, we have several numbers too. The first number is the range. The range is from the lowest value to the highest value. Okay, I just take the highest value minus the lowest value, and I will have the range. If you remember, we do not usually use the range. Why? Because the range is usually quite wide. Okay, if you remember those distributions, the range starts from here and ends here. But this is quite wide. I just need the most important half of this distribution. How is it distributed? Okay, if the most important part is from here to here, that's better than having the most important part from here to here. Okay, why? Because when it is from here to here, okay, it will be a bell shape. But if it is from here to here, it will be more flat. Do you agree? Perfect. So you can see here that the distance between the median is a number in the middle. The quartile, the upper one and the lower one, are the number in 25% from the lowest value or the highest value. Why is this distance between the mean and the upper quartile smaller than the distance between the upper quartile and the highest value? Because the frequency here is lower than the frequency here. Okay, so if we just return them to the line and just extend the line, we will have the difference between those higher than the difference between those, because those are really dense. They are close together, but those are not close together. Okay?
Okay.
So,
can you repeat this part? Sorry.
okay, yeah, exactly. Of course. We usually take the most important part, and the most important part is usually the central half of the data. Why is it the most important part? Because it represents most of the central cases. And why is that important? Because they can represent the data better than those in the periphery. Okay, those in the periphery might be like exaggerated data. Those patients do not actually follow the standard of our population. I usually care about the central part. Okay, so if I care about the central part, I care about the variance of the central part. Why? Because if I have the central part, the 50% of those participants from here to here, the variance is quite lower than if I have those from here to here. Okay, although the range is still the same. Okay, so if I have the range is still the same, okay, and I have them like flat. But what does that mean? That means that the space between the quartiles is wider. But if it is like more lower in the periphery and more higher in the central part, we have the interquartile range lower than the other case. Is that clear?
It is. Thank you.
Okay. So we have those two numbers, and we usually use these numbers with the median because they follow the same rules. Okay, they follow the order, but I don't usually use the mean with interquartile range. Okay, sometimes I do, but usually median is followed by the RQR. Range is quite rare. The other thing is mu. Mu represents the mean. Okay, usually with the mean I use standard deviation. What is standard deviation? Standard deviation is calculated in a very complex way, and we don't need to understand it because the program will calculate it for us. But the main concept of standard deviation is when it is a normal distribution but when I have mu minus a standard deviation to mu plus a standard deviation, okay, it's 68.2%. Okay, and if I take another standard deviation to the right and another standard deviation to the left, I will add till I reach 95.4%, and so on. If I add more, I will have more percentage of our data. So if the standard deviation is wider, what does that mean? That means the variance is wider. And if it is smaller, then the variance is smaller. And this shape is more convex. Is that right?
Can you repeat the question?
Okay. So the standard deviation, I usually use the standard deviation with the mu, which represents the mean. If I have a big standard deviation, then I will have a higher variance For example, here, if the standard deviation is still here, okay? What do I know? I know that this tip is not like here, it's here, and the shape is like, okay.
More flat.
Flat.
Draw. Okay, more flat. Yeah. This way, the standard deviation will be wider, right?
Right.
And the two standard deviation will be more wider, and so on. So the mean with the standard deviation give me a quite understanding of
About the variance
and how we can make it normal. Okay. But what sorry, I didn't understand your question. Is a question. Okay. So here we have it in a similar example.
So,
yeah, please, Ahmed.
So when curve is more flat, it is no more normally distributed, right?
Exactly. And if it is more pointed and if it is more convex, okay, then it's not normally distributed as well. If I have a really small standard deviation.
Okay.
Okay. So if we move on, we have those percentages, and they are represented by those lines that represent first, second, and third standard deviation. And here we have a new concept. This is the standard deviation, and here we have from 2 standard deviation to the left and 2 standard deviation to the right. This space is the confidence interval. Okay, so the confidence interval and the standard deviation are quite similar, or we can take one from another. Okay, because 2 standard deviation up and 2 standard deviation down means the confidence interval. Okay, why? Because we have this 95%, and if you remember, for each confidence interval they usually say the 95% confidence interval, because we have a confidence interval for 68% and we have a confidence interval for 99.7%. So we should define which confidence interval we are using. We are using, most likely in every paper you are going to read, it will be 95%. Okay, so what are those 2.5% of the data? Since I have 95% of the data in my confidence interval, then upper to the confidence interval I will have half of the rest, which is 5%, and lower I will have half of them, which is 2.5. Is that clear till here?
Yes.
Perfect. That is perfect. Okay. Is that fine? If you remember, for the categorical data, we started with the pie shape, but sometimes we don't have a pie shape or a pie chart. We have those column charts. Why? Because we have 2 variables. Okay. If we are going to add another variable here, it will be like this column. But if we are going to add another continuous variable, it will be so complex. So let's start with the first part, adding another categorical variable. What does that mean? That means if I have group A and group B, okay? Group A will have a distribution and group B will have a distribution. Okay, those distribution might come together and might be far away from each other. Is that okay?
Yes.
Okay, so we have two groups. If we have two groups, we have two distributions. And why do I have two groups? Because I might have males and females. I might have those with intervention and those without intervention. I might have cases and controls. Okay, so if I have two, if you remember, for categorical data, having two variables means 2 by 2 table, because for each variable I have two options, and two options, it will be 2 by 2 table. So having two options here, what does that mean? That means that I have two bell shapes, and by two bell shapes, we might have some complexity showing up here, and we might have not, right? Can you tell me what is the difference between this and this?
One showing overlap in the distribution, other are like mutually exclusive.
Exactly, but why? Why is it like this?
There are a causation between them, like some of the people who get intervention might get the control if we do blinding or something like that.
Yes, Maarouf, you are right, but this is a conclusion. I'm asking about the etiology. Why does it appear like this in the first place?
I didn't understand what you asked exactly.
Because there are causation or there are correlation between the two groups. They are not separated.
Yeah. Just wait. That's so complex for this phase. Yes, Maya, do you have any other answer?
Yeah, so the first, the separated bell-shaped, okay? So they are, okay, they don't affect each other. So I'm not gonna be like so sophisticated, but yeah, by this, it's still ideal. And in real life, we will not have it, okay? But the one on the right or the left, sorry, so it's more realistic and it will include the false positives and false negatives. So yeah.
Okay, I understand you all, and all your conclusions are right, but I wanted to say that for the first part on the left, for those two bell shapes that overlap, well, we have either one of two options. The mean difference between them is so tiny. So those bell shapes are really close to each other, okay? Or the variance is higher for each of those two distributions. So they are still here, but the distribution is higher, so they overlapped, okay? I hope you are seeing my face because like I'm representing them in my hands. For the other chart, we have those small Gauss distribution, not Gauss distribution. Well, we are saying that those are distributions because we don't know if we have Gauss distribution or normal distributions here or not. For those, we either have really or quite big mean difference, or we have very little variance, okay? But what is the mean difference? Mean difference means that if I take the mean of the intervention group and the mean of the control group and put a minus sign between them, the resulting number will be really high. Okay. The other thing is the standard deviation or the confidence interval. If I'm taking this and make it wider, they will have the overlap they have in here, okay? So the change from this to this is either one of those two things. the mean difference or the variance. Do you agree?
Yeah.
Okay.
Can
But
you
please,
repeat how?
yeah, please, Yusra.
Can you repeat how we calculate mean difference?
How we calculate mean difference? Yeah, it's just a minus between them. I take the mean and just the distance between them.
Yes.
Okay.
Okay.
So it's either the distance, the mean difference, or the variance. Okay. But by saying that, what do I mean? I mean that if I have a higher sample or more participants, what will I have if I have more participants? Less variance or more variance?
Less variance.
Exactly. Why? If you remember,
Yeah,
if
it's
we
more.
multiply the bell shape, it will have less variance because it will grow more in the central part.
Yeah.
Okay, so if I have this overlap, I should do either one of two things. Adding more participants, so I have less variance and I reach this, or I, for example, increase the dose of my intervention. For example, if I increase the dose, the difference will be higher. For example, if I'm giving a drug for blood pressure and I give another pill of this drug, I will have higher effect. By higher effect, I mean more mean difference. Okay, so this is how I reach from this to this, and we need to understand that. So we go on. Yeah, please.
Sorry, I just a question. In the real life, like how statistically significant is this? I mean, in a research, would it be better to have a control and an intervention that have such statistics or such difference? Meaning, which is better actually, this one or this one?
Actually, I don't usually have those two options. Okay, if I have one of them, that would be perfect. Okay, because for the variance, I can recruit more patients, but I am limited by the ethical approval of my institution. For the intervention, if I give more of my drug, that is actually limited, of course, because I might give more, but if I'm giving more, I don't expect the variance to be the same. Of course, when I'm giving more, the variance will increase because those patients will not just react to my additional bill in the same way. So I'll have more variance. So it's a balance. If I have one of those interventions to make them like split from each other, that would be perfect.
I see.
But
Thank
it's
you.
too perfect to be true.
Exactly.
Right? Good to be true.
Okay. And to tell you the truth, should be calculated. Those numbers should be calculated before I start my experiment. Okay, because those numbers are representing the power, the alpha error, and the beta error. So I should calculate them and calculate my sample size according to them. So I reach this after I do my experiment or my intervention, not this. Okay, because if I do it and I reach this, I should report my data. And if, for example, another doctor is going to do the same experiment next time, he will know that my mistakes were either low sample size or the difference wasn't quite high. So he will work on one of those things, okay, if this is feasible. Okay, how to report that? Here we have two groups. Yeah, any question?
So the more overlapping the two curves, the less accurate the results.
Exactly. And we will discuss that in more detail next session.
No, it's about Ibrahim. It's not about the accuracy, right?
Sorry. Maybe I didn't understand your question quite perfectly.
It's not. He said that when I'm having overlapping, okay, so it's less accurate. It's not about the accuracy of the results. So here you're talking about like,
Precision.
okay, about, yeah, precision and sensitivity and specificity, but it's not, it's different from accuracy, right?
Yeah, exactly. Actually, for the precision, I'm saying that what will represent the precision here? It's the standard deviation and the variance, okay? Because when I take more samples, I will have lower error and lower variance, so I will have higher precision. So here we have higher precision than this. But as Maya said, for accuracy doesn't mean that. Accuracy means that when I'm assessing, the intervention group is not actually here. It's here, but I found out that it is coming here. And this is not accurate, okay? Accuracy is getting the right number, but precision is getting it more frequently. Okay, is that clear? Does that answer your question, Ahmed?
It does. I didn't mean accuracy literally in the way you defined before, but okay, I got the idea.
But we have accurate participants here. You should take care next time. I should take care, actually. Okay. For here, if you remember, we put one table where we reported the mean and the standard deviation, or the mean and the confidence interval. Here, in this table, we have two groups, two intervention groups, a placebo group and the hydrocortisone group. Here we have the number of cases and we can add the percentage. This is categorical. But if we move here, that number that represents the pulmonary infiltrate, and it is continuous. And here we have a number and a confidence interval. And as I said before, we should define the confidence interval with that number, 95%. And we put it like this. Okay, here we have a number and a percentage. Okay, so this is how I report continuous data when we have two groups. Now, what we did is reporting categorical data for one group, categorical data for two groups, and continuous data for one group, continuous data for two groups. Does anybody has any question to here? Okay, perfect. Here we have another table, the mean and the standard deviation. When I'm putting the standard deviation for two groups, here we have the seizure groups and the non-seizure group. When I put the standard deviation, I either put it into brackets or I put just plus minus and I put them. Here I have the same mean and the standard deviation and so on, number and percent. And I believe like 90% of the tables we are going to read in the papers we read will be including one of these numbers, okay? They won't have more complex numbers, okay? But for the figures, we should like learn more, and we'll discuss that next session. So for the hypothesis, I can start with the hypotheses actually right now, or we can just take a little break and discuss it in the next call. What do you think? Just please put a thumb.
A break, please.
A break. Anybody has any suggestion?
I vote for a break.
So we meet in 10 minutes maybe. Okay.
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 Have fun in your break. We meet in 10 minutes.
Okay. While you are reading, you interpret standard deviation and confidence interval as the same thing?
They're not the same thing, okay? But they represent the same thing, okay? They both represent the variance.
So you interpret it in your mind as the same thing, the variance.
Exactly.
Okay.
But of course, in the same table, I shouldn't put like sometimes the standard deviation and sometimes the confidence interval. I should use the same number for each table.
Because
it will be easier to understand. For example, if I put here mean and standard deviation, and here I put confidence intervals, it will be like complex or not easy to read.
okay.
Okay, so sometimes I have some preference to confidence interval, and sometimes I will have more preference to report a standard deviation, but it's like quite mixed. Okay, so we shouldn't think about it because they represent this, the main thing, and it's a quite simple course.
Okay, thank you.
Okay, you are so welcome. So I see you in 10 minutes. Goodbye. So, do we have any question before we start the third part? Maybe we should wait for 1 minute because we are having the number where. Okay, welcome to the last part. I hope you find it easy to understand the last two parts. And yes, actually they are complex, but just learning those basics will make it easier for next sessions. Of course, we can repeat whatever you want next sessions before we do the analysis, but having a good understanding of them right now will be much better. And for the hypotheses, first we should understand that everything we believe in and everything we see in life might be a lie. Of course, we can't be sure 100% about anything. We can understand that. Okay, and we have errors. What are those errors? We have two types of errors. The first type, when we say something is right and that can't be right, or when we do not believe in something while it is actually true. Okay, so we have the truth, and I like this pen. Okay, we have the truth and we have the test or our experience of that truth. Okay, sometimes the truth is positive and we think positive about this. So it is right, and we think it is right. So that's correct. Okay, we are fine. Sometimes it's not right, okay, and we don't think that is right, and that is okay. What is the error? When does this error happen? For example, when we have something that is actually true, okay, and we can't see it, or we don't believe that is true, okay, and this is called type 2 error, okay. False negative. By false negative, I mean false means that my opinion is false and I believe it is negative, so it relates to my opinion, okay. It can't be false positive because false positive is here and it goes to my opinion. The truth can't be false, but my opinion can be false. So the false positivity and the false negativity belong to my opinion. If we move on, what is the null hypothesis? The null hypothesis is when I come to you and I tell you before and after these sessions, we will be the same. We won't learn anything, okay? Why do I tell you that? I tell you that because actually I don't believe in it, but I need to prove that this hypothesis is wrong, okay? If I succeed to reject this hypothesis, then I can conclude that you learned something, okay? I can't directly tell you that we will learn something, okay? In evidence, we can't prove something is right, but if we can prove that something is wrong, then the alternative might be right, okay? So, for the null hypothesis, I would, for example, these cats do not have any preference for the shape of their food, or those two plants do not prefer any of these two colors, or age doesn't affect playing the violin. Okay, so this is the null hypothesis. I think those interventions doesn't mean anything to our participants, okay? But if I find out that this plant that is growing under a red light, okay, is growing much slower than this one that is growing under a yellow light, then I say that my hypothesis is wrong. There is something wrong, and then I conclude that those plants have preferences for the color of the light. Okay, is that clear?
Why can't we prove that something is right, and why do we have to prove it by rejecting its opposite or its contrary?
Okay, okay. If I give you those two shapes, okay, you can't prove that there is no errors in here, okay? Of course, you can say there are something here that is right, and there are something here that is right. But how will you know that this thing is going to be your conclusion? Okay, you might be standing here, okay, in the middle of those errors, okay. Actually, just let me continue to this next slide, and you will understand it better, okay. Okay, so for each test we are going to have, we need to put a null hypothesis, and if we succeed to reject this null hypothesis, we will accept the alternative hypothesis. What will the alternative hypothesis be? If I say that the null hypothesis, these cats do not prefer any type of food, the alternative hypothesis, they should complete or be exactly the opposite. Those cats do have preferences, okay? But I can't say that if the null hypothesis, they do not have preferences between food, and the alternative hypothesis, they prefer fish food, okay? It should be don't do or not yes, okay? So I can't specify something in the alternative hypothesis, and when I reject the null hypothesis, I accept that, okay? It should be conclusive. So,
is there a reason, or it's just like that? It can't be.
of course. Look, they should complete each other. By that I mean that we have just two bell shapes, okay? If I have more than two bell shapes, I can't use this, reject the null hypothesis and accept the alternative, okay? If you have, for example, if you have that alternative hypothesis of preferring yellow light and preferring red light, okay? And the null hypothesis means they do not have any preferences, okay? What alternative hypothesis should you take? You can't take any. You should take, if they do not have any preferences, the alternative hypothesis should be they have a preferences, okay? Well, without specifying anything. But of course, the null hypothesis can be these cats prefer yellow light, okay? And the alternative hypothesis, they do not prefer yellow light, okay? It can be another different comparison, and in this comparison, we can just specify the yellow light or the green light, okay? But we can't specify something while the null hypothesis is not specific. Is that clear?
It is.
Perfect. So there is some point that I need to run towards, so I can reject the null hypothesis. And we are going to define what I'm running after to reject this null hypothesis, okay? This is just a scheme, and that doesn't mean anything, but for example, for this, okay, we have a question: will you marry me? And the answer says that, can anybody tell me if we can, what is her answer? Yes or no from this sentence?
I don't know for sure.
Sorry, Ahmed, can you repeat your answer?
Yes.
I think we don't know for sure.
No.
No, yeah, exactly. Why? Because she is assessing. Okay, yeah, please, if you have any comment.
Yeah, because we failed to reject, so it's the null hypothesis. It's right. So
okay, so if the null hypothesis is right, if I fail to reject this null hypothesis, then I won't change anything. Okay, then I don't have any point of my research. Okay, I'm doing my research. So she said I failed to reject the null hypothesis. So she has those opportunities to get married, and she's looking for this part to reject the null hypothesis and to get married. Okay, so she won't marry from anybody here. She will marry just if she can reject the null hypothesis. How is it like this? Okay, if you come to some person and you ask him, am I the right person for you? You can't be quite sure you are the right person for him or for her, okay? But you can say that according to my distribution, to the distribution of the people in my mind, you are better than most of them, okay? So I will reject my null hypothesis and I will say that you are not one of them and I will marry you. Okay, if I reject to do that, then you are one of them, and I can't marry everybody. So yeah, you are rejected. Is that clear to everybody?
It was before the example.
Okay.
And there
Failing,
is a question
failing
on the
to reject is accept, isn't it like that?
Yeah, but this is the example. This is why I brought the example. I failed to reject the null hypothesis, not the conclusion. Okay? When I fail to reject the null hypothesis, then I consider the null hypothesis right. Okay. Now,
How can I conclude the null hypothesis from the question?
From the question, okay.
Will you marry me is, how can I conclude the hypothesis from will you marry me?
Okay. The null hypothesis is that this person is similar to everybody. Okay? If that is right, I cannot marry somebody who is similar to everybody. Okay? I need somebody who is different,
okay.
or who is like distinct in some way, or he has something, so I marry him. Okay? So the null hypothesis is this person is not special. He is like everybody. So I will test him. If he is different, if I can prove that he is not similar to everybody, I will marry him. If he is not similar to everybody, then I shouldn't. Right? Okay, let me repeat it. Let me repeat it. I have several people in my mind. Okay, if somebody comes to me, and he asks me, "Am I the right person for you?" I can't prove that he is or she is the right person. Okay, but I can compare her or him to the people I have in my mind. Okay, if he is just similar to one of them, then I shouldn't consider him or her. But if he is like really special, then I should consider him, right?
Right.
Being similar to everybody is the null hypothesis. Being distinct or special is the alternative hypothesis.
Yeah.
So I can't prove that he is different, but I will test him. Is he similar to everybody? No, he is not. Then he is special. Okay, does that answer your question, Ahmed?
It's more clear than before, and I think I will judge at the end of the session.
Okay, okay, and I believe nobody will understand it unless he spends like 1 or 2 hours just by himself understanding it. Okay, so that person came.
The null, like, it means there's just no relationship, or there's no relation between them.
I just have a question,
Because
please, Doctor.
Name is null, so there's nothing.
Yeah, for Zara, yes. For Massa, can you ask your question?
It was Nawara, I guess, not me. I wasn't talking.
Oh, I'm sorry because I can't see everybody. Who can ask? Yeah, who want to ask?
I wasn't asking. I was just stating something.
Okay. Is it clear to you, Nawara?
Yeah, the null hypothesis. It means there's no relationship between the two stuff.
Exactly. Exactly. So, any other question?
Massa, you have a question.
Me, please.
You have, yes.
Yep. Please. Does the null hypothesis should be more specific, or which one should be the more specific here?
Okay.
The null or the second one?
Actually, there is no specificity in them, okay? They are just like yes and no. This person is similar to everybody, not similar to everybody, okay? And I can't prove he is not similar in a good way. He might be not similar in a bad way, okay? And you will understand that more in the examples that will follow, okay? So I have those people in my distribution. Some of them are better, some of them are worse, okay? And I have that proposal. So I can't say that this person is from a very good population, okay? From compared to the population I have in my mind, but I can say that this person is in my population or is included in my population, or he's not, okay? If he is not, then he is better or worse. I can't prove that, okay? So the null hypothesis is this person is no different from my population, my community, or this person is, sorry, the null hypothesis is similar. The alternative hypothesis, this person is not similar, is special, okay? I hope.
It's fine with me.
Perfect. So, Massa, if you have any other question, you can just stop. So she broke his heart. Okay. What is the type 1 error and type 2 error? Okay. Now, we have the null hypothesis, and we agreed that we have the truth. Null hypothesis is true or false, I don't know. And I have my options or my decision, rejecting the null hypothesis or failing to reject the null hypothesis.
Please, just 1 second before we move, because there's something on the chat.
Okay.
Okay. Okay, Basel is saying, you're saying it correct, but a tiny thing to add if that helps. Null difference, but not significant enough.
Sorry,
Alternative
your
difference,
answer
but
was
significant.
due to
Yes, Massa.
What's happening now?
I don't know. Massa, if you hear us, just tell us what do you want. Okay, thank you so much, Basel. Let us hear your voice. Okay, so maybe we can move on. We have type 1 and type 2 error. Okay, now we understand the null hypothesis and the alternative hypothesis, and we have the errors. Okay, am I sure about the null hypothesis and the alternative hypothesis? Which of them is right? No. In reality, they might be right and they might be false. And in my decision, they might be right and they might be false. So we have the same two errors. False positive, when I think the null hypothesis is rejected, okay, and I accept the alternative hypothesis while that is not correct. And the type 2 error, which is false negative. False negative means that I don't reject the null hypothesis while it is false. Okay, and we can spend on this slide the time you want. Do you understand the two types of error? Actually, the false positive, that I'm coming to somebody and I'm saying that you are pregnant, but he can't be pregnant, okay? The null hypothesis is true. He is not pregnant. He is similar to everybody, okay? But I'm saying that he is pregnant. He has something special, okay? So I rejected the null hypothesis from my opinion, but the reality, the null hypothesis is true. Or the other type of error, I come to somebody who is special and who has a baby, and I tell him, here, you do not have a baby. So I fail to reject the null hypothesis. I say that you are not different. You are like everybody in the population, while she is actually special. Okay? Is that clear?
For me, it is.
Okay, just please use the thumbs because we are going so complex right now. Oh, perfect. Okay, then I have my decision and I have the truth. Except null hypothesis equals, I'm not able to reject the null hypothesis. Accepting the alternative, okay, the null hypothesis is H0, the alternative hypothesis is HA. Accepting the alternative hypothesis means being able to reject the null hypothesis and accepting the alternative hypothesis. Okay? Okay. While in the truth, they might be reversed if I have any type 1 or type 2 error. Okay. Now we understand the error and we understand the hypotheses. But what should I do? How does that apply to statistical tests? Okay, statistical tests, or at least the statistical tests we are going to learn in the first 3 sessions, will be on categorical data or in for continuous data. For categorical data, for example, I have this variable. This variable says that we have 4 categories. Okay, this is categorical data. For those categories, if I take a sample of any population in the world of humans, okay, the proportions will be like this. Okay, let's say those are I don't know. Okay, let's yeah, it can be. Okay, so we have these proportions. If I take the sample from, or not if I take a sample, if I take a very big sample that can be representative of all humans, or if I take actually the whole population, okay, they have this proportion. Then I went and I took the population of my study, okay? I went to take, for example, rheumatoid arthritis patients, okay? I took them and I observed that the numbers are like this, okay? What does the statistical test means? I give these numbers to the statistical test and I tell him that the normal proportions should be like this. So he takes those percentages and apply them to my sample. My sample, let's say, for example, 300. And he has the expected frequencies, okay? So now he says that if anybody takes any sample of humans that includes 300 participants, he will expect these numbers, okay? These numbers in the last row. These numbers are the numbers expected by the statistical test, but I have these numbers. What is the statistical test going to do? He will compare them, okay? If these numbers are similar to the expected frequencies, then we can't reject the null hypothesis. And
yes, we accept
the null hypothesis. They are similar, and our population doesn't have any distinct categories. But if these numbers are not similar to the expected, they do not match. There are for example, A is truly high or D is truly low, then they do not compare. Then we reject the null hypothesis, and by rejecting the null hypothesis, we accept the alternative hypothesis. What does the alternative hypothesis say? the population I took is not similar to the whole population. Okay, so rheumatoid arthritis patients have distinct categories for this variable. Is that clear?
Yes.
Anybody else? Just please put, okay, that's perfect. Yeah, please, any question? No question. Okay. So we have the test results, and when I'm saying that I'm doing the statistical test will give me the number, but will give me something that says those are similar or those are not similar. What is this number is going to give me? He will give me a number that represents the probability of being similar or the probability of not being similar. He won't tell me that they are 100% not similar. No, he will come to me and tell me that the similarity between them is quite high. I estimated with about like 70%. Okay, they are similar by 70%, then I can't reject the null hypothesis. But if the statistical test comes to me and says that they are similar, but the similarity between them is just low as like 2%. Okay, so for 2%, I can reject the null hypothesis, but for 70%, I can't reject the null hypothesis. Okay, the statistical test compare them and give me a probability of being different or the probability of that they are the same or they are just different for a little bit by chance. Okay,
So is there fixed numbers to tell me if I should reject or accept?
okay, well, we will talk about it next session, but it's 5%. Okay, it's the p-value. Okay, it's exactly the same p-value we will define next session, but what is it? It's the chance of similarity between these two frequencies. If it is quite high, then I can't reject the null hypothesis, but if it is less than 5%, I can reject the null hypothesis because I say that it's less than 5% chance that those are similar. Then my population is quite different from humans in this variable. Okay, so when this statistical test give me the number, this number actually applies to this types of error. Okay, so I still might have that error. For example, if this number tells me that I can reject the null hypothesis, then I reject the null hypothesis. Sorry, yeah, I reject the null hypothesis and I accept the alternative hypothesis. I'm here. Okay, and it is right. The actual value is the null hypothesis can be rejected. It's false. Okay, but of course I can be false positive. Okay, if I'm like 5%, okay, it might be like this, but the chance is 5%. The statistical test comes to me and he tells me that you are 90%, 95% safe, but we still have that number. Okay, if the statistical test comes to me and tell me that both the groups are similar and the similarity is quite high, I estimate the level of chance with 70%. So I reject the null hypothesis, 70%, but I still have 30% chance my group is different, but I'm not detecting it. Okay. So I hope this is clear, because I need to run to the next one. How does that apply here? We have, okay, let me tell you that the third and fourth lines are categorical data. We have here 23 out of 24 who passed the exam and 18 out of 90. Okay, and here for the third group, we have 19 out of 21. We compare them, and the statistical test tells me that the probability of similarity is 74%. Then I don't reject the null hypothesis. Those three groups are really similar. Do you agree?
Yes.
I hope you agree. Similar to the conclusion here. They are similar, so I don't reject the null hypothesis, so I accept the null hypothesis, and the null hypothesis says that the third, second, and first year are quite similar in this outcome. There is no distinct thing going on here. Okay. But what about continuous data? Okay, I understand here, when you give me some data, the statistical test will compare them to the expected data and tell me what is the chance of probability, what's the probability of chance. But for continuous data, he will take the mean of my observations and he will compare it to the normal distribution of humans. Okay, if I take the age of humans, it will distribute like this. Okay, and if I take a sample of my city, okay, let me take a sample of 100 patients, 100 people from my city, and I found that the age is 2. Okay, then the statistical test will take the 2 and compare it to the normal distribution, and after that he will tell me that what is the probability of chance in me getting 2 if I take a normal sample of all humans. Okay, here we can see it more clearly. We have the normal distribution and we have no doubt about it. Okay, I took a sample. My sample is standing here. Okay, it will be smaller, but for simplicity, I take that sample. That sample has a mean of, like, its mean, sorry. Its mean is here. Okay, so the statistical test will compare this to the null hypothesis, and he will tell me that the chance here of getting any higher ages is quite low. Okay, but if my mean is here, okay, he will tell me that 30% you are getting this by chance, but here it's like 1%. Here I can reject it, and here I can't reject the null hypothesis. Okay, but of course, as you remember, here we have errors, and here we have errors. We are standing here, that's right, but I might be wrong, and I might belong to the null hypothesis. While I rejected the null hypothesis, I'm standing here and the probability is 1%. So I said that I will accept the alternative hypothesis while I have 1% chance of belonging to the null hypothesis. But if I'm standing here, I won't reject the null hypothesis, but of course I will have like 10%. You can see here, yeah, you can see here that I have 10% of false negative, okay, that I belong to the alternative hypothesis, but I couldn't make it there. So errors are here and here. If I'm here, I will have type 1 error, false positive, if I belong to here, but I consider it false. And if I'm standing here, I will have type 2 error because I couldn't make it to the alternative hypothesis. I couldn't reject the null hypothesis, but it is actually rejected and I belong to this. This is a mess. Okay, how does it apply here? And I believe this is the last slide. We have here continuous data, continuous variables. We have means. We have means. And here we have the number of participants. And we have the probability. The probability is quite high, 41%. So I can't reject the null hypothesis. I'm saying that those means are really slightly different. And this is by chance. This is even more a chance. Those are more similar than the first line. And if I get like this is, for example, 30. This will be 0.02. So I put a star. I say this is quite low. I have 2% chance. Then I will reject the null hypothesis. This group is not similar to those two. Thank you. We are done.
Thank God.
So, we are done with this session, but this is just the beginning. Okay, what do you think? Do you have any questions?
I have. Does it relate to the numbers like 0.6? May I reject the null more than others?
Actually, we put the cutoff before we do the experiment because that will introduce bias. For example, if you do the statistical test and you get 0.06 and you haven't already decided on the level of significance, the 0.05, then you might like see it enticing to change the cutoff of yourself to do it like 10% and make your statistical test significant. Okay, then you can do it, but this is biased. So that's why we usually use the 5% for every medical study, but for example, for some genome-wide association study, they might use a level of accuracy that go down till like 1/1000. Okay, so but we need to define it before, and I compare. All my examples were for 5%, but it can be 1/1000, it can be 10%, it can be whatever. But the usual standard is 5%. Does that answer your question?
Yes, it means we should follow the guideline or something like that. We can't decide by our own.
You can decide by your own, and they will decide by their own to reject your paper. Okay.
But does it mean like getting 0.68 is more getting wrong than 0.9?
No, 0.68 means that you are here, 0.9 you are here, and 0.9 is like here. Okay, so they are no different because you are still in the null hypothesis, but the probability of alternative hypothesis is higher when you are in 0.69. Okay, for example, the 0.68 means that you have 32% chance that the alternative hypothesis is right. Okay, but when you are 91% here, then yeah, you are just 9% rejecting the alternative hypothesis while it is right. Okay, so they complete each other.
It means the more the percentage is more closely to the 0.9, the less error I get.
The less type 2 error. Okay. Okay. Any other question? Yeah, please, Ahmed.
So I got what you said about the null hypothesis and the alternative hypothesis, but I still can't understand why can't I prove the thing for itself rather than proving it by rejecting its alternative or its opposite.
I'm really sorry. Can you repeat your question, because I couldn't hear it very well?
I want to believe. I want to prove the alternative hypothesis. That's my intention. Why do I have to believe it by rejecting the null hypothesis? Why can't I prove it?
Okay. I give you those 3 numbers. I have those 3 means. Okay. Tell me, how can you prove that this number is different from them? You can't unless you compare it to the numbers, to the other numbers. Okay. Yeah. For example, sorry, where did I go? Okay. But for example, here, if I don't give you the null hypothesis, okay, it's not like this. Can you tell me that that your mean is quite different from the from the usual mean without comparing it with the null hypothesis with the usual number? Yeah, you have that number, and I have the usual number of this. Okay, can you tell me this number is quite different without comparing it to this number?
In this particular example, I can.
Okay, so I need to compare it to the null hypothesis. I will take another example. I will take the example of continuous categorical data. And here, okay, yeah, you have those observed frequencies. Okay, they are different from each other. You have this very low percent and this very high one. Okay, how can you tell me these observed frequencies are different from the population without comparing them to the populations of to the expected frequencies of the normal population, and telling me, okay, there is quite low probability of being similar to them, then I will reject the null hypothesis and say this is true.
Okay, I see your point now.
Okay, so thank you so much. I'm glad you understood it.
Me too. That I understood.
Thank you so much. Okay, any other question?
Can I ask a question?
Of course.
The area of positive false error type 2, why there is a part of it above the row of null hypothesis? Oh, the other one. Yes, here.
Yeah, here. You mean
why there is the part of type 2 error above the row of null hypothesis row? Yes.
Okay, those. Okay. You are hitting on the spot. Do I know where to put my line? I don't know, actually. If I know that line, that will make it really easier to reduce the amount of error. But usually I have those two populations and I'm not quite sure where to say it is the alternative hypothesis that is right and the null hypothesis that should be rejected. Okay, for example, and what does this line represent? I will tell you because we just discussed like 5 minutes ago. This line represents the 2.5%. Do you remember them? If I'm saying that my cutoff, if you remember the question from Maarouf, if I'm saying that I will take the confidence interval of 95% and the error of 5%, okay, you understand now that the confidence interval is 95%, then the error can be up to 5%. And if it is 99%, then the error can be 1%. Okay, and so on. So I told you that I accept a chance up to 5%. Okay, then I'm telling you that this number will stand here. If I'm saying that I will accept just 1% chance, I will put this line here. Okay, what does that mean? I will reduce the amount of false positive, but I will increase the amount of false negative. Okay, although it will be like till here, all this will be blue. Okay.
Okay.
Do you understand now? Do you understand me now? Because this line I can be quite sure where to put it.
That accord to confidence interval.
Yeah. When I define my confidence interval, okay. Look. I'll put my confidence interval, and I put this like 5%. It will stand like here and here. And when I have my mean, if it is like 4%, 3%, 2%, 1%, or lower, it will be important. And I will reject the null hypothesis. If it is 6%, I won't reject the null hypothesis. Okay, so this is the difficulty in here, deciding where to put the line.
Yeah, thank you.
You're so welcome. Any other question? Yeah, please ask questions because we have time.
I want to ask, can we use the concept of null hypothesis and alternative hypothesis interchangeably?
But how? Or why should I do it? For example, null hypothesis, there is no difference, and alternative hypothesis, there are difference.
Yes, but what if I want to just change the names because one of them is just easier for me to calculate?
You can say that the null hypothesis, your population is different. You can't.
Okay.
Okay?
Okay. Yes, thank you.
You're so welcome. Any other question?
Last question, if you allow.
Yes, Ahmed, please.
When you were reading the p-value, you interpret it as probabilities that the null and the alternative hypothesis are similar, that the two populations are similar. That is how you interpret the p-value when you are reading papers.
To define the p-value, well, we will discuss that in more detail in next session, but the definition of p-value is the probability of getting my result by chance, considering the null hypothesis is true.
Okay, but just when you like when the p-value was like 0.74, you said that this means that 74% that the two population are similar by 74%.
Yeah, when the p-value is 70%, then we are standing here. Okay.
Okay.
Then 70% is the null hypothesis is true, and the populations are similar, and 30% they are not true, and I belong to the alternative hypothesis.
So 30% will be in the the blue and the yellow area, right?
Okay. Now I'll tell you. As I move left, the p-value will increase till I reach here. It will reach 1.
Exactly identical.
Okay. And it will be so small here. So if you remember the graph when we put just two Gauss distribution, and I told you if I need to make my test important, I should move this line here to increase the mean difference or add more participants and reduce the amount of overlap. Why? Because if I reduce the amount of overlap, being here will have less p-value than being here when we have a lot of variance.
So I have less chance of error?
Exactly. Less chance of error, less overlap, lower p-value, higher power.
Overlapping represents the areas where I'm going to get errors.
Exactly. This is the overlap, and those are the error. The yellow is the type 1 error, and the blue is the type 2 error.
Okay.
Remember, type 1 error is false positive. And here, to the right of this line, I'm saying the null hypothesis is false, and I'm saying there is a difference. Then I am false positive. Here on the blue line area, I'm saying that the null hypothesis is right, and the alternative hypothesis is false, while I am wrong, while it is true. So here, yellow means I am saying you are pregnant and you are not. The blue is I am saying you are not pregnant while you are.
Okay. Okay, thank you.
You are so welcome. Any other question? I'm so sorry that we discussed that while we have just 11 participants. Yeah. Have a nice evening, and you are so welcome. Yeah. See you in 2 days. Goodbye.
Bye.
Thanks a lot.
You are so welcome.